Shwanta, you had a question about why the two definitions are the same in the perfect field case, right? The two definitions of varieties being defined over a subfield F. Is that correct? Have I understood it? Rather, you had a, why is it true that, some system of linear equations, you posed it that way. But in the end, that was coming from, in any case, I will say something and tell me if this answers your question or does not answer your question, in which case you tell me what the question is once again and I'll come back about it. Yeah. So F is a subfield of an algebraically closed field. So X says a variety over K. So we think of this as points over K. I mean, at the moment, you can even think of an affine variety. Okay, so let's say X is an affine variety. So it is given by the zeros of certain set of polynomials over K. But what does it mean to say it's defined over K? That is, so one possible definition is that X is the zero set of bunch of polynomials with coefficients in F. So in appropriate number of variables, if this is living in A to the n, this is, I would say, this is a bunch of polynomials with appropriately many variables. That's one way to think about. Or you can think about, another way to think about is that, so that brings us to the next thing. Namely, more abstractly, you can think of Kx, and there is a variety there is a affine algebra, reduced affine algebra Fx, which when I tensor with K, I get Kx. So the ideal of X is extended from Fx. From the polynomial ring over F. In other words, this is true, right? So this, what is this? This is polynomial ring modulo the ideal over the ideal Ix, the ideal of X, this side. And if this is true, then that means that I take the ideal over all the elements in Fx that vanish over X and extend it to Kx, I get the ideal for Kx, the ideal Ix. Okay. Now the thing is that these two are equal. So we are considering these two conditions, 1 and 2, right? The claim is that these two are equivalent when F is perfect. So you call F perfect if, let's recall, in characteristic 0, all fields are perfect. In characteristic P, this means Fp equals F. By this we mean I take elements of F, raise them to the pth power, and look at that set. That's a subfield that you can easily see, right? If that subfield equals F, in other words, every element of F has a pth root in F, such a thing I call perfect. Okay. So the claim is that these two are equivalent when F is perfect. So what you have to show, of course, if this is true, then this is true, right? Because if Ix is extended from this, second is an a priori stronger condition, right? So certainly 2 implies 1. The problem is to show that 1, if I assume just 1, then I do get 2. Okay? So the thing to observe is the following. Again, I am not so here is what you have to show. So if I'll say this as exercise, right? So F perfect field then any reduced commutative algebra over F is separable. Of course, this is a new word for you perhaps. I'm introducing a new word, separable. I have to define what it means, right? An algebra is called separable if a tensor, let me use L, I extend the scalars to L, where L is any extension field that continues to be reduced. So if A tensor L over F E is reduced for every extension field L of F. So I repeat, so you have, okay, so this definition in algebra A, okay, over a field F. Okay, just to make that complete. Is the statement clear? So, and okay, let's just give some example, just so as to make it clear why this is. What is the so? And then this is the problem, right? To check that a reduced commutative algebra is separable. Okay, I am claiming that answers this question. So and that is the exercise, and the solution to the exercise is, you can try it yourself, is in the notes that I mentioned on my web page, if you want to look at it, but maybe you should try it by yourself. Okay. Okay. Now let us make some more comments as to what the meaning of this is. Okay. What do you understand by separability? If from your field theory you understand that separable means no repeated roots, right? It is the same idea, just that it is just put here abstractly. So you have to understand, we have to understand why that simple idea of no repeated roots is comes in here like this. Observe in particular that A itself is reduced, because F, I can take L to be F, in which case I get back A, and that is reduced. So if I have a separable algebra, it's clearly reduced. It has to be reduced. The claim is, if it is a perfect field over a perfect field, if it is reduced to begin with, then no matter how much I extend, it will always be reduced. That's the claim. Okay. So let's observe. Okay, so let me give an example. Suppose I take K, let's take round bracket T and then an X. So, and characteristic of K equal to P. If I do this, so what do we understand by this? It's K is a field. This is rational functions in one variable. That is my base field, right? This becomes my F, and I adjoin, this is polynomial ring in one variable, and go modulo this, right? This is an algebra, right? It's a finite dimensional algebra over this field, right, of dimension exactly P, because 1x x to the P minus 1 is a basis for this. Okay. Now, is this separable? Okay, no, because why not? So this is the typical case where separability fails, because if I attach a root, what does it look like? It looks like a pth root of x. I'm going to attach x to the 1 over p, and the moment I attach that, this will factor as t to the 1 over p, not x to the 1 over p, t to the 1 over p. I attach the pth root of t. The moment I attach that, this x to the p minus t will split as x minus that pth root to the power p. Okay, so it's an irreducible polynomial here in this field. Again, that's an exercise. You can check that that's an irreducible polynomial here. All these exercises are done in those notes. Okay, I mean they are done elsewhere too, but so it's an irreducible polynomial which has repeated roots. Okay, so that you can see because also because the derivative test, by the derivative test, if I take the derivative of this, that becomes 0 in characteristic, because we are in characteristic P. Okay, so this is a non, it's a reduced algebra, it's even a domain, right, because this is an irreducible polynomial. Okay, but it is a non separable algebra, is not separable, since so let's call it A. A tensor kt adjoint t to the 1 over p. Right, this is the field. I adjoin a pth root. This is equal to, okay, let's call this some other name, capital K maybe, right? So K x by x minus t to the 1 over p to the p. Correct?
There is also A. And your K is also.
Is that all right? What I've written? This capital K.
Is that equal to? Wait, is that so adjoining bth root of t is what is A? Adjoining bth root of t to kt.
Yes.
So
Yes.
so essentially A tensor A. So A tensor A over K tensor A over K.
You could say that. Indeed. That's a good point. Absolutely. Absolutely. So, indeed. Very good. This is, you can think of that as A as well. Yeah, absolutely. Yeah. This is non-reduced. As a, since Gautam brought this up, how about this? What is that equal to? It's a standard exercise in when you study tensor products. Is this okay? So it's exactly what along the lines you were thinking. You think of one as a polynomial ring, the other thing as a field, but one as a Rx modulo x square plus 1. So you can think of this as, the way to you can analyze this is by just putting this, and that will become Cx over x square plus 1. Now this is not a domain anymore, right? This is, we know this is Cx by x minus 1 cross Cx by x plus 1. Sorry, x plus I, x minus I, right? But that is reduced, right? That's reduced. So in fact, that was what is involved in that our other, if the group has no p torsion, then the group ring is reduced, right? The idea of that proof is the same as saying that if involves something like this, right? So this is so you can say C is a separable algebra. So this notion can be in particular applied to when A is a field extension of F. Okay? For example, this one, as Gautam points out, is a field extension. This field extension is not separable. This field extension of KT is non-separable, whereas C over R is separable. Okay? So, and by this, any field extension in characteristic 0 is separable. Okay. So if you do this, it might seem like I'm introducing more and more notation and terminology rather than clarifying a point, but it is rather useful to have this terminology and notation once and for all straightened out and settled, right? So like I said, it may be good for you to just look at Bourbaki, if not immediately, but sometime in the near future. That will you can once and for all be done with it. Okay. Now, okay. So at the moment, I'm just pointing this exercise out. Okay. Is that good enough, Shananta, for the moment? That was your question, right? This. I understood as this as being your question. No? Not quite?
The question was that if it's not a perfect, so how do you show that dxf is k tensor over f? Dx is k tensor over f dxf.
Say that again. If f is not perfect, then how do you show?
That dx is isomorphic to dx.
T, what is T?
Standard space.
Oh. Ha. Okay. Okay. In that context. Right? This is what
Why is this isomorphic when f is not separate?
f is not perfect.
Perfect.
Okay, this was your question. Okay, sorry, yeah, now I remember that you asked this. Okay, no, I don't think perfectness should enter there at all.
Otherwise, like, if I don't have a finite set of polynomials, which generate the ideal of the variety, like how
Yeah, but this is not, I mean, you don't need to think like that necessarily in this case, because it's all it's all linear, so to speak. The situation is linear. In any case, I will, sorry for having misunderstood your question. I will answer that next time. I'll definitely think about that by Friday. Okay. As to the other one, I did think about the other pending question. I thought about it, but still don't have I gave it some thought, but I still don't have a satisfactory solution. So that is pending. And I'm aware of that. Okay. Hopefully by next time I would have had time to settle it. Okay. Now, any questions on what we were doing?
Last time we took an example of the curve of y square equal to x cube, and then for that we saw that modular differential is omega I over k. How do you see that that is equivalent to that I mod I square definition?
How do you? Well, directly you mean? See, that has the universal property, this has the okay, directly. Okay, I don't know. I don't know off the top of my head. I see what you're saying. I mean, you want, on the one hand, it was sort of defined in a calculus kind of fashion. It was a free module, modulo certain relations which were directly related to the equations defining the variety, right? That is one way we did it, and then we claimed, and I'm going to prove it in gory detail, this I mod I square business, which we were at towards the end I messed up with so we'll do that. So good question. I don't know the answer. Okay. Of course, as we all realize, I mean, you could just fall back and say both have the universal property, but a better answer than that I don't know at the moment. Okay. Okay, last time I messed up this proof, so let us work through that proof, okay? Because it's algebra that may be just a little bit sophisticated. So let's, at any rate, we'll just work that out. So the claim was that I had to construct this. So what was the notation? R was a commutative ring, always with identity, and A was a commutative R algebra. Right, and we had to construct this universal module of differentials, right, which has this universal property, namely that there is a natural R derivation denoted DAR from A to that, which is universal in the sense that you give me any A module M and an R derivation from A to M, then there exists a unique A module map from here to here that makes the diagram commute. In other words, so it solves the following problem, so to speak, derivations, R derivations from A to M. So M I can use as a dummy, so I'll put a blank, is equal to HOM as A modules from right. So it is the object which, you can pose this question where I put the same dummy variable here and say, can I fill this blank in? And indeed you can, and this is the thing, right? And how did we, so as we observed, from the way it is posed, it is clearly unique up to unique isomorphism if it exists. So we are only reduced to showing existence. And what did we want to do about existence? We said that look at the map A to A. This was like the diagonal. Think of, if you think geometrically, this should somehow be the diagonal embedding of whatever A is the ring of functions of, say X, if it's the ring of functions on an affine variety, this would be the diagonal of X sitting inside X cross X. So this was, and look at I is the kernel of this map, and claim was this, along with a natural construction of a DAR, will do the job. Right? Okay. So let's write down. So we want to prove that indeed that such a thing holds. That if I take omega AR to be I by I square and DAR from A on A to be 1 A tensor 1 minus 1 tensor A, this pair I mod I square along with this map has the required universal property. This is what we have to prove, right? So we'll just go through the details quickly. Hopefully this time I will get it right. Okay. So let's see, what all do I have to show? Okay, now why is this map? So I'll pose these as questions. So why is so let's ask, it should be an R linear map. It should be an R derivation. So in particular, it is R linear.
Firstly, when you say I mod I square,
Huh.
we are thinking of it as a A tensor A mod I module.
Okay, yes, indeed. Okay, let's why is this an A module to begin with? Okay, even before, correct. So let me step one back. So thank you. So I, of course, to begin with is only a, I itself is only an A tensor A module. Because it's an ideal, I is the kernel of this map. Right? Being a kernel of a ring homomorphism, it is a two-sided, it's an ideal, it's a commutative algebra. A tensor A is a commutative algebra, so I can say it's an ideal. It's an ideal in A tensor A. Right? Okay. Now, so this makes sense as an A tensor A module, but then this is killed by I. So the module structure descends to A, right? So even before that, so I mod I square is an A module. Because I kills I mod I square. And moreover, let's observe one thing. When we say it's an A module, the crucial thing that enables the calculations is the following. How does A act on I? Right? How does A act on I? If I take A in A and some, so suppose I take A in A and some, say something of the form Ci tensor Di, something like that. This is in I. Rather I mod I square. Let's put that. How will A act? Can I put A Ci tensor Di, or do I put Ci tensor A Di? Which do I put? The answer is either, right? Because what does it mean? It means that you choose a pre-image of A in A tensor A, which you can do either A tensor 1 or 1 tensor A and then multiply it out. Okay, so this is equal to either A Ci tensor Di bar or Ci tensor A Di bar. Either one is okay. It's easy to check that the difference belongs to I square. The difference of A Ci tensor Di of that with Ci tensor A Di is Ci tensor Di into A tensor 1 minus 1 tensor A. So Ci tensor Di is in I by assumption. A tensor 1 minus 1 tensor A is in I clearly, and therefore their product will be in I square. So another way to okay. So is this okay? Does that answer your question? Okay. Okay. Now why is this map R linear? So let's do it here. So let's look at A to A tensor A. There are two maps, right? A going to A tensor 1 and A going to 1 tensor A. Both are R algebra maps. Right? So both are R algebra maps. So the differences are linear. So A going to A tensor 1 minus 1 tensor A is no more an R algebra map, but it's clearly is R linear. right? Okay. Now let's do, okay, so let's check that it's a derivation, right? So it's an R, so far where are we? This is an A module, this is an R linear map. Let us check that this is a derivation, okay? So sorry, the board is, I hope you can see it. It's not erasing, it's a derivation. Okay, so what do I have to show? I have to see if, so let me forget the A over R, so let me call this just D to avoid cumbersomeness. So what do I have to show? I have to show this is B, so this is the question mark, I have to show that, plus right? So let us expand both sides and see what I get and just observe that they're same. What is D of AB? D of anything is definition AB tends this, right? So it is AB and with a bar, right? To denote it's in I mod I square. This is AB tensor 1 minus 1 tensor AB bar. Is that equal to, right? This, what is this? This is B, A tensor 1 minus 1 tensor A, right? Plus A of B tensor 1 minus 1 tensor B, bar. Right, this is what we have to check. Okay, let's see. Okay, let me decide to put this A in the first place. Okay, so this is the same as AB tensor 1 minus A tensor B bar, right? Now let me put this in the second place, just for, I'm free to do that. I have to put a bar. Right, what do I have? And I have what I want, right? Because this cancels with this. I have AB tensor 1 minus 1 tensor. Right? So that's what, okay. Now let us, okay, so we are done with the, this is, so far we have that this is an A module and this is an R derivation, right? Okay. Now then I have to show that this has this universal property given an M and an R derivation. Now let's call this capital D. Right, I have to show that there exists a map here. Right. Okay, so let's try that. So why? So let's call this D tilde. So how do I define D tilde? Okay, so I have to define D tilde on I, right? How are we going to do that? It's a problematic, right? See, you can't just define see, it's a submodule. It's sitting in, it's a subquotient of A tensor A, right? So if you look at it that way, it looks quite impossible to see how to define it. The way, one way to get around the problem is to define it on A tensor A and then restrict it. Okay, A tensor A, remember, now has the universal property. It's a tensor product. So to get a map from A tensor A to M, I just have to give you a bilinear map from, right? So let me do that. So define d tilde from A tensor A to M. Okay, let's see what I want. It should be an R linear map, right? So given by A tensor B going to, okay. See, what do I want? I look at this and decide what I want. See, this is the image of A, right? I want this to go to D of A, right? So let me see, when do I get D of A? If I put the second one times the D of the first one, I do seem to get that, because this one will become 0, because D of 1 is 0. Okay, so that gives me the motivation. So at least it tells me that I should try this. So let me try that. So at this point it exists. This d tilde exists. Why? Because now this I claim is an R bilinear map. It's bilinear in A. It's linear in A and linear in B. That's what I have to check. It's linear in A because D is linear, right? And R, it's a, so if I put R here, R comes out, and that R comes out again, right? So it's linear in A and it's linear in B. Therefore, there is this map, right? Okay. Now I can restrict it to I. Okay. Restrict d tilde to I. Right. Now claim d tilde restricted to I square is 0. See, we are not claiming anything about, see, at this point, at this level, we are not claiming anything about the A linearity of d tilde. Okay? I mean, because this is not even clear. It's an A module, all right, but it's an A module in maybe one, two, many away. Namely, it's on the, with these two, there are these obvious A module structures. Okay? So, we are not at the moment, we are only going to do it when it is at the level it is required. Okay? And probably nothing more, because, so, restrict, okay, so I have to check this, right? I have to check this. So let's see how to check this. Okay, let's see. So I take something in I square. Okay, there may be other ways of checking it, but let me just do it, I don't know, brute force. Okay, I take, what do I have to check? I take two elements of I, multiply them, and check that d tilde. If I apply d tilde, I'll get 0. Okay. So I take two elements of I. What do I? So let I write them like this: AI tensor B maybe to the I, just to keep track of lower and upper indices. I can put a. So let me take a Cj tensor. Yeah, so that's a capital D. So I can use a small d here. Dj, both in I. Right. Now, what does this mean? Let's keep track of that. The fact that this is in I means right? That's what I is in the kernel. I is precisely the kernel of that multiplication map. So that is true, and so is this. Right. Okay. So let's try to use that. So I'm going to erase this one here. Okay, now let's apply d tilde to this product AI tensor BI. Okay, now that's what I wanted to omit the notation, the sigma, with some physics kind of convention. So Cj tensor Dj, right? This is what I have. So I should apply. So first multiply them. I get AI Cj tensor Bi Dj. Right? Okay. Now this is equal to, what do I have? I have second one I write in front. And then apply d to the first one. By definition, that's our definition of d tilde. A tensor B goes to B times dA. Okay. Now this is a derivation. I am given that. Okay. Let me use the fact that it's a derivation. So what do I get? I get Bi dj. This is A sub I. Sorry. Okay. First, let me do the Cj dA sub I. Correct? Plus the other one is Bi dj Bi dj, correct. Bi dj Ai dCj. dCj, correct. Correct? Okay. Now was that 0? Well, there is this dj Cj here. That is this 0. The other one has Ai Bi. So this is 0 because of this. And here, these two here. So B I A I equal to 0. So, right, okay. So we have that. So indeed, d tilde, what can I say about d tilde now? D tilde restricts to I mod I square, and it's an R linear map at the moment. I have to say that it's an A linear map, right? So still I have to show that d tilde is an A linear map, and it lifts is obvious, right? Because the way I have defined it, so find thank you. So thus d tilde okay, why is this A linear. Right, I have to check that. What is it on, how is it defined on I mod I square? Well, I can take, if, so I'll do this briefly here. So if I take, let's say, Ci tensor Di bar, okay, that's an element of I mod I square. This goes to Di dCi. Right, that's the definition of d tilde restricted. Okay. Now, what is, so I have to check that this is A linear. That is, if I multiply by A on this side and A on this side, then it's consistent. Now, what do? I observe that it is A linear, this, I can use either one, whichever is advantageous. Okay. So, I notice that A of Ci tensor Di bar with the bar is equal to Ci tensor A Di bar. I use that one. Okay. And where does this go to? A Di dCi, and that's what I want. Okay, so we are done. So that indeed is A linear. So this is checked. Okay, is anything remaining? So d tilde lifts D. So are we done, or is there something that remains? The chalk piece problem.
I think so.
I just see if கீழே ஏதாவது ரூமில் ஒரு பாக்ஸில் இருக்கா பார்த்துருவேன். இல்லை நீ எடுத்துன்னு வரடா அந்த பாக்ஸ் ஒரு வெளில பாக்ஸ். தேங்க்யூ. D tilde lifts D. By that I mean this diagram commutes. Right, that's not a problem, because if the way it was defined, this will go to dA, right? So that's not a problem. So anything else that we should do, or are we done? Uniqueness. Indeed. Huh?
We already gave the argument that we just have to reduce the case of showing just existence.
No, existence, that map is unique. There is, yeah, it's correct. Once we show that map is unique, this is uniquely defined. But we still have to show that D tilde is unique. Okay, let's see that. Okay, is that? Okay, so uniqueness of D tilde. Okay, subject to what? It lifts D. Thank you. Okay, this will. Yes. That really helps. Thanks. So let's see. Let's try it out informally. What all do I want? I want. So this will go to. So what do I have to show? I take some element like this, say of I, and I have to show that it has two properties. It lifts d tilde and it's a linear. It's a map from it is 0 on I square and it's a. So with these properties it must be unique, right? Okay. Now from the fact that it is a linear, what can we deduce? Let's see. So this, put a bar there just to keep track that I'm in I mod I square. So if I, so wherever this goes, if I multiply a, put a here, that a must come out, right? That's what a linearity means. And I also have this. I have so d tilde on a tensor 1 minus 1 tensor a bar is clearly d of a. There is no choice about this. That's the fact that d tilde lifts d. Okay, let's see. That along with the a linearity, okay. The other thing is to try and show that these elements generate I mod I square as an A module. We could try and do that. So let's just try that. Okay, I will try for 5 minutes. If we can't do it, I'll again ask for a deferment of the proof. Okay, so the fact that so this is Ci di. So sigma. Let's just work with a single C and D and C just for the sake of argument. Once we do this, we can jazz it up to the more general case. So I suppose I know that CD is 0. That's what I know, right? For it to belong to I. Okay. What can I do? I can take C. So I should maybe C tensor 1 minus 1 tensor C bar with a D. Okay, what do I get now? This is C tensor D minus 1 tensor CD and then I can put a okay, what's the difference now? Yeah, one tensor CD, and one tensor CD is 0. CD is 0, right? So here, so C tensor D bar I can write as D times this. So actually, so this I claim is equal to this. This is a very special case when CD, if CD is 0 for a minute, okay, then I claim this is true. Why? Because what is this? I can put the D here and I can put the D here, but CD is 0, so this goes away. So indeed this is equal to this. Okay, so let us use this to see if this idea works. So I have Ci tensor Di. I know that Ci Di is 0. Here I omit the sign. So let me try Ci tensor Di, okay, bar, okay, bar D I. So I can write as Ci tensor, let me see if I can manage this. Okay, now is that okay? I've just added a one tensor 0. Just check if you agree with me. Okay, so indeed that shows that elements like this are, so what we have showed is, so what we claim is, so we have shown I mod I square is generated as an A module by one tensor A is in A. Right? So that finishes the proof. Okay, good. Okay, so this was an exercise in sort of module theory. Okay, as I said, this lemma 4.2.4, I expect you to read. I will not cover it because we've seen the idea of that, right? It is how to write the module of universal module of differentials for the ring of functions of an affine variety, right? So it is the quotient, so you think of it as for the affine space in which it is living, that will be a free module, and then you go modulo relations which are DFs, where F1, F2, Fn are the equations defining the ideal of the, right? It's a very natural, most natural thing, right? Whatever, like I was saying, it gives, yes, Gautam, you had a question?
If I have a tensor
So you can so you can think of the module over A itself. So you take a module over A. So you're right. So when I said that, it can be a little confusing, because what am I taking the module over, right? The module, of course, you can take over the polynomial ring or over the quotient ring A, right? So I meant you take a free module over the quotient ring A. That's like pulling back the cotangent bundle from the X. So X is the affine variety. It's sitting inside AN, right? So, and our A is K of X. R is K, and we are interested in constructing omega A over R. That is omega of this ring of functions over K, right? So first is to think of a free module over this, with very suggestively the generators of the free modules will be called dx1, dx2, dxn, where x1, x2, xn refer to the variables here, to a set of indeterminates here, functions. And so that is like pulling back the cotangent bundle from here to here. Okay? At the moment, you've only pulled back the cotangent bundle. So if you are doing it with, you are taking a free module over the polynomial ring, you are doing the cotangent bundle here. If you are doing the free module over the ring A, then you are pulling back the cotangent bundle to X, right? Now, then if you go modulo the relations, then you are getting the cotangent bundle of A, of X. Okay. Is that clear? Okay. So that will not do. Now, let's go on to the next section. Not next section actually. So he says, let's discuss the case of fields. Okay, so we have, so F he wants to denote by a field. So instead of K, I guess the notation now is F, because it need not be, there is no assumption of algebraic closure that is required, perhaps that's the reason. And E prime and E are two extensions of finite type. Okay, let's keep that. So then we have this exact sequence. So let's see, derivations. Okay, it's better to take E. Well, E prime is contained in F, E. Right. So this is the assumption. Okay. So I can think of E as an algebra over F, also as an algebra over F prime, right? Okay. So um, that is just the restriction map, right? This is just the restriction map. I restrict an F linear map from E to E to E, the F subspace E prime. Okay. Now, what is the kernel of this map? The kernel of this map is all those F derivations that are 0 on E prime. And what did we observe? If you have a derivation, F derivation to begin with, a priori only F derivation, which is 0 on E prime, I claim it is linear, E prime linear, right? It's a derivation. Derivation just means Leibniz rule, right? Leibniz rule holds. So let's just check that for a minute. So if I have a derivation D, and if it is 0 on E prime, right, then I claim it is E prime linear. Why? Because if I have D E prime E, by the Leibniz rule, this is E D E prime plus E prime DE, but this is 0, therefore it is E prime DE, right? Okay. So, and conversely as well, right? If it is so if it is an E prime linear, it's going to be a derivation, E prime derivation from E to E, right? So if it goes to 0, then it's an E prime derivation, and if it is an E prime derivation, surely it goes to 0, right? So this is the exact sequence that we have. So this is the inclusion, natural inclusion. This means the Leibniz rule holds. This means also Leibniz rule holds. The only difference is this is F linear, which is a weaker condition than saying E prime linear, which is a stronger condition. So this is naturally a sub included there. Okay. So we have that. Okay. Now let us. I erased this, which was written here. Let's translate this to so what is derivations of E to E? So we know that Hom right? You agree that this is the same as this, right? Okay, Hom E Hom okay, let's see. Right. Okay, so how are these the same as this? So there must be a natural. Okay, so this is what as you know, Hom is, so we are homing into the first variable, right? Hom over E over E prime is an E module, yes?
E prime E is an E prime module. All of those are E prime modules. I have always
Okay, so let's see. Right, so so let's put an X. Suppose I do this. Okay, then I claim, let's find this out. Okay, what is this? This is X of DAB, and therefore that is X of BDA plus X of ADB, which is, I can write B of XD on A plus A of XD on B. So what does this prove? It's like that, I don't know if you may be too young, or maybe that show is still there. There was a show called Jeopardy on TV. I don't know if you have watched this. So, okay, maybe it's only in the US that it's popular. So where there is a quiz, it's a quiz where the questions are posed as an answer, and you're supposed to guess the question. So similarly, what is this the proof of? That this is an A module. That this has the structure of an A module. So indeed, this has a structure of a E module. A is exactly. Here we are assuming A is commutative. Yeah, we are assuming that. Okay, I checked with my other notes the notation. I mean the convention. So there also it's assumed that it's commutative. Okay. I repeat. So derivations are also useful in a non-commutative context. For example, for Lie algebras, etc. But I really have not, bothered to go the whole hog and see how far those assumptions can be extended. In any case, at the moment, it's not of relevance to us. We are assuming A is to be commutative. A is commutative. Okay. Right. If you have a non-commutative ring, then homomorphisms between modules, for example, does not have a ring. There is not a module. Okay. So things are pretty bad anyway. So it only has the structure of an abelian group. Okay. So this is so is that okay therefore? Okay. Right. So where were we? So let us understand this. How do we get this? So this is okay. So rather this, you should think, we are trying to understand this, and I'll write down something from which we will, okay. So it is natural to expect that if I have a thing like this, then I do have this, right? I mean, at the moment, just think of this as somehow this is the same as this is the same as this is the same as this, and there should be natural maps here, okay? And this should be exact as well, right? This is what we expect. But let's understand this from the viewpoint of these universal derivations. Okay, so what do I expect? This must be this harmed into the. We are using this as the first variable, which is contravariant. So there should be an exact sequence in the reverse direction, right? So what I mean is this. No, I've reversed arrows, so therefore. Okay, is there a map like that? Well, there is a map like that, right? That's the universal derivation. It is E prime linear. Therefore, in particular, it is an F derivation. Therefore, by the universal property of omega EF, there is a natural map, right? Okay, so this is natural map. There is a unique natural map, right, which makes this diagram commute. So this is d E prime by over E. This, of course, is d E over F, and there is a natural map here, right? And this is onto. Okay, here I don't like the proof. Why is it onto? Okay, I'll give you a proof that I don't like. The proof is from the observed from the construction that the D, okay, so from the construction, and this is the part I don't like. I don't know, I should not feel refer to the construction, but that's the only proof I know at least at the moment. From the construction, what we know is that if I have A DAR is surjective. What do I mean by that? No, let me say like this. Image of DAR generates as an A module. Why was that? Because it was I mod I square, and that was A tensor 1 minus 1 tensor A, right? And we saw that, in fact, I mod I square is generated by elements of the form A tensor A minus 1 tensor A as an A module, right? So that justifies that. Okay. So this map therefore is onto. Why? Because all the elements, so these elements are, this diagram commutes. So this map, this is, what kind of a map is this? This is an E linear map. So this is a module map of E, and all the generators are already here of this are already in the image. Therefore, this map is onto. Okay. I would like to know, if please do think about this. Can you prove this without reference to the construction? That would be nice. Okay. Okay. So, and what do we have? We have another. We have this. Right. Again, that is natural. Let's see. How do we get this map? right? This is, so at the so I have all this, right? We have all that, okay, and this is an E prime linear map. It's a map of E prime algebras. This is an F linear map. This is an F derivation, right? So this thing is going to be an F derivation, right? From here to here is an F derivation. Because, so one thing to remember is if you a linear map and or an algebra map and a derivation together give you a derivation, okay? So this is a derivation. That's an easy exercise. And all the more reason, okay? Yeah.
Leibniz rule and linearity just follow because E prime is subset.
Fine. Okay. Thank you. So this is clearly a derivation. So by the universality of this, there is a map here. Okay. Let's see what now. Right. So I have this, right?
You want you need to make E over F to be E prime mod.
Is that okay? Yeah, this is an E prime linear map.
No, you needed omega E over F to be an E prime module.
Yes, E prime module. It is an E module. It's even an E module. Therefore, in particular, it's an E prime module. Okay. So we have that, right? We have the, so this is, these are the natural maps here which makes this diagram commute. Okay. The claim is now that this is exact. I want to claim that this is exact. Okay, let me see here. Could I replace this with right?
What maps are these? And what kind of maps are these?
These are E-linear maps. Okay, so let me for a minute. Okay, so for a minute, let me can I can't I do that? For the same reasoning, so it's an F derivation from E to M. The E prime derivation from E to M is surely an F derivation from E to M, and for it to be an F derivation from E prime to M, rather this is the restriction map, and it goes to 0 if and only if it's an E prime derivation, right? Same reasoning, right? Okay. So okay. So now let's start over again. Suppose I had all this, and M was an E vector space, then I have this exact sequence. Okay. So keep that on the one hand. I have this on the other.
So you just said that omega E prime over F is an E module.
I didn't say that yet. No. No, omega E over F is an E vector space.
Yeah, but prime over F is not an E vector space.
No, not yet. No, it's not. Okay, correct, not. Okay, not. Okay, so you have this picture here, correct? Okay, now what I want to claim is that I want to claim that that is exact. Say abelian groups or E prime vector spaces. Okay, I want to claim that's exact. What is the proof? The proof is I hom into let's see, I put an E prime, right? Maybe I get into trouble here. I want to say E prime vector spaces I want to claim, okay. Maybe, okay. One more step perhaps. Right, okay. So let me, to remedy the situation, I do want it to be an E module. So what I do is I can, instead of that, write also if you have an E prime, this is an E module. This is an E prime module, and I have an E prime linear map. Therefore, there is naturally a E linear map from this to this, which X, right? So, I mean, if you have, say, R and, okay, let's take A and B. Right? I have a B module N, an A module M, and an A module map from B to N. Say B is an A is a B algebra, B is an A algebra. Then there is, so this is an A module map where you think of N as an A module by pulling back the structure. Then there is a natural map from here to here. Now this has a B module. Okay, so using that idea, I do get that there is a, right, okay. Now claim is this is exact. So I'll finish, oh my God, I'll finish. Okay, and the proof is an exercise. Here is the proof. So this is what I want you to work out. That's the exercise. To say that something is exact, okay, enough to show that hom E star, let's call this star M is exact for all E vector spaces M. Right? And then when I okay, so right now this was just motivation. I have on the one hand this, but now this is there for the moment, keep it. I also have this, right? I want to claim that this is an exact sequence of E modules now. Shayanta was complaining, so I've changed this to this now, right? So as E modules now, as E vector spaces. So I have a sequence of E vector spaces, I want to say it is exact, and the exercise is to say that to say something is exact, enough to show that it's exact after I form it with any m. Okay, that is okay. Now, what do I get when I form it with m? I do get this, but that's the same as this, but I know that's exact. That's the proof. Right, good question. Now, what in this thing that I wrote, so here is another exercise. Form E of E tensor omega E prime over F to M as an E module is equal to form E prime omega E prime over F. Good. Right? Good point. Right? So
So this thing
I
as
huh?
an E prime vector space. This equality is
That equality, no, even as an E vector space, because the latter gets, even this gets an E vector space structure from the second. So for example, if I take an phi here, what is E times phi? You define it as E multiplied on phi of whatever, because that makes sense, because M is an E module. Okay, that does get an E vector. I can even say as E vector spaces. Okay, very good. See you then on Friday.